We're very excited about our speaker today. I saw her TED Talk could be found on TEDx London Women, and we all watched it. It's amazing. She's amazing. Claire Malone is our speaker today. Her fascination with understanding the fundamental laws of physics led her to pursue research with the Atlas experiment at CERN, based at the University of Cambridge, where she is a student. Through her experience in that field, she developed her passion for making physics accessible to the general public and for also improving the STEM-related field for LGBT people and people with disabilities. Her TED Talk can be found, as I said, at TEDx London Women. And Claire will stay behind after the assembly to answer your questions. So very pleased to have you here, Claire Malone.
Hello from London, everybody. Thank you to Laura for inviting me. Today I would like to show you how finding partners for fundamental particles could solve some of the biggest problems in physics. But who am I? I am a member of the High Energy Physics Group at the Cavendish Laboratory at Cambridge University, searching for new particles using the Large Hadron Collider, LHC, at CERN. I am also passionate about sharing my love of physics to make it accessible to as wide an audience as possible. At school, I was the archetypal geeky kid, wanting to just get the other lessons out the way, so I could get into the science labs. After school, I went to Imperial College in London, and graduated from there with an MSc in physics in 2014. That's a photo of me on my graduation day, and it is clear evidence of the fact that, if you do too much physics, your hair turns purple, so be warned. I am currently completing a PhD in particle physics at the University of Cambridge, and sometimes I get to go to the European Organization for Nuclear Research, CERN. Some of you may have seen it on the news a few years ago when they discovered the Higgs boson. If you haven't, maybe go and check it out, because particle physics is really cool. See, I told you I was a geek. I have also been various shades of queer, and have been actively involved with the LGBT societies at Imperial, Cambridge, and CERN. I have currently settled on being pansexual with she/her pronouns. I have to say that I have generally had a very positive experience of being female and LGBT in STEM, and the LGBT group at CERN were particularly supportive during my time there. However, my physical disability, cerebral palsy, has had a much greater impact on my career as I generally dictate all my work to an assistant. The idea of dictating equations and code may sound strange if you have never had to do it before, but if you have been doing it throughout your education, you find techniques to make it work. I also completed lab work by giving very detailed instructions to my assistants about how to use the equipment. A small complication with this is that I was having to describe things that I had never physically done with my own hands. To get round this, my assistant and I met outside school hours to practice how I was going to dictate my practical exam. To begin with, He would go through the steps of setting up and performing the experiment whilst verbalizing what he was doing. When I had got an idea of how I was going to explain how to perform a variety of experiments verbally, we practiced with me giving the instructions. The framework that describes the behavior of the particles which high-energy physicists study is called the Standard Model of Particle Physics, or SM for short. The SM describes fermions, which are the particles that comprise matter, and bosons, which are fundamental force carriers that mediate the interactions of the fermions. Fermions are divided into quarks and leptons and are arranged in 3 groups called generations. So, as shown on the slide, the first generation would consist of the up quark, down quark, electron, neutrino and electron. The particles in each successive generation have higher masses than those in the previous one. The bosons of the SM mediate the fundamental forces that act on the fermions. Photons for the electromagnetic, M, force, W plus or minus and Z for the weak force and gluons for the strong force. The M force governs the interactions between electrically charged particles via photon exchange, while the weak force can transform one lepton or quark into another, provided it is in the same generation. This is the force responsible for radioactive decay. The strong force is responsible for transformations between different quarks and is the force that holds protons and neutrons together. One of the particles you may have heard of is the famous Higgs boson. The particle gained its illustrious reputation by escaping detection for the longest, until its discovery in 2012 at CERN. The discovery of the Higgs boson is crucial because it provides the mechanism through which all the other particles attain their masses, even though the more fitness-conscious particles may disapprove of its activities. The SM even has a child-friendly version, in the form of soft toys for each of the particles. Some of these particles, many of you will be very familiar with. The protons and neutrons in the nuclei of atoms are comprised of up and down quarks. The nuclei of atoms are orbited by electrons, which play an essential role in many physical phenomena such as electricity, magnetism and chemical bonds. Photons are the quanta of the electromagnetic field which is responsible for all EM radiation. However, other SM particles may be less familiar even though they are around us all the time, and in some cases crucial to everyday life. It would be pretty tricky, or impossible, to form protons and neutrons and hence atoms without the gluons holding the quarks together. Gluons are, of course, not to be confused with the warlike humanoid alien species from Star Trek. Life as we know it would also not exist if nucleosynthesis in the Sun did not fuse hydrogen into helium and other heavier elements. However, despite this coherent picture, the SM does not provide us with a complete description of the particle content of the universe. It actually only provides a description of just 5% of the universe, having nothing to add about the remaining 95%. It is one of the main aims of the LHC to remedy this major shortcoming. So how do we know that most of the universe is unaccounted for? We know the observed rotational velocities of galaxies alone suggest that the total mass of the galaxy is far greater than can be accounted for by just the luminous matter. This missing mass has been termed dark matter, and is predicted to account for 23% of the energy-matter density of the universe. The SM can offer no suitable explanation as to the character of this dark matter. In addition to this, the unexpected discovery that the expansion of the universe is accelerating, rather than decelerating due to gravitational attraction, points to the existence of a previously undiscovered force acting against gravity on a universal scale. This force, which accounts for the remaining 72% of the energy density of the universe, and is now known as dark energy, also has no explanation within the SM. The SM also does not explain why the universe is dominated by matter particles, rather than containing equal amounts of matter and antimatter. Finally, there is a gap of 32 orders of magnitude between the largest and smallest scales in the SM, which seems quite unnatural. A possible solution to some of the ailments of the SM is offered by SUSY. SUSY is now one of the strongest candidates for the explanation of physics which is not accounted for by the SM. SUSY extends the SM by postulating a supersymmetric particle for every SM particle. These particles possess identical quantum numbers to their SM counterparts, except for a half-unit difference in spin. They also have, in the true tradition of particle physics, very silly names. In honor of the name supersymmetry, a supersymmetric particle becomes a. In honor of the name supersymmetry, a supersymmetric particle becomes a sparticle. The supersymmetric top becomes a stop. For reasons I shall explain, I am particularly interested in finding the stop quark. But how can these so-called sparticles solve the problems we've found? Well, remember we said that we were missing a load of dark matter that is meant to be floating about in galaxies, keeping their rotational velocity constant with the distance from the center as is observed. We hope that the sparticles could be what this dark matter is made of. But if dark matter is made up of sparticles, it must mean they are really difficult to detect, otherwise astronomers would have spotted dark matter before now. Also, the fact that they have not been found by such sophisticated experiments like the LHC, would suggest that they don't interact with our detectors like normal particles do. In fact, this is what we are counting on when we search for sparticles at the LHC. We know that conservation of momentum must hold for every particle decay, otherwise something is really wrong, and we may as well go to the pub. So, if we don't detect enough energy from the products of the decay, that must mean that the sparticles have stolen it, and not been detected. I said that I was particularly interested in finding the top's partner, the stop, and on the slide you can see a diagram of a stop decaying to a top, after the protons have collided at the LHC. The particle on the right-hand side of the diagram is a SUSY particle, called a neutralino. As she is the lightest particle, so decay chains stop when she is produced. She is often named as a suitable candidate for dark matter. The stop quark has a special role to play amongst the squarks. I mentioned that there are 32 orders of magnitude between the biggest and the smallest energy scales in the Standard Model. As a consequence, there is no explanation of why the observed Higgs mass is much smaller than the value we would theoretically expect. The mass of the Higgs can be thought of as the sum of the masses of all the other particles, and the top quark has the biggest contribution to this sum because of its large mass. This is where SUSY comes to the rescue. When we consider all the sparticles, as well as particles, we find that their contributions to the Higgs cancel out the contributions of the particles, to leave a nice, light Higgs. As the top is the heaviest particle, the top and the stop have the biggest contribution to make to this cancellation. We can think of it as a tug of war between SUSY and the Standard Model. The SM wants to pull the Higgs mass way higher than the mass we observe, but luckily SUSY is there to keep everything in balance. This is why, if physicists can discover the stop and other sparticles at SEN, it would be very exciting, both from the point of view of finding a description of dark matter, and also explaining why the Higgs is allowed to be so light. So why do I spend my life looking for hypothetical particles that don't interact with any of our detectors? Well, certainly for me at least, the prospect of finally having a complete picture of the universe, in terms of its fundamental building blocks, is more than enough motivation. Or it could be just to justify adding a cuddly toy universe to our particle toy box. Thank you for listening.